All right, another type of question that AP loves are these velocity selectors. And we talked about this in class. Obviously, again, they love it because it combines both an electric field and a magnetic field. And so we have one of those here. You can see the battery that's connected to our parallel plates here. And so we know, for example, that the positive side will be connected to the positive plate here. And then the negative side will be then connected to the negative plate because there's extra electrons there. And so we've got our electric field here, and we can actually already figure out what the electric field will look like, right? Because we know that the electric field always shows what would happen to a positive charge, so the electric field would kind of go up like this. All right? Now, the questions are asking for the magnitude of the magnetic field, and then the direction of the magnetic field. That's essentially what these two questions are asking for. You can read through the whole thing, but everything's basically here. So here we go. We're going to try to work through that. So for the magnitude, we know that we need the force of the magnetic field to be equal to the force of the electric field. Okay? And we've already shown that the electric field is going this way. So we need the force of that field. We're going to need to figure out what that is. Now, that's pretty straightforward because we actually know from our formula packet that the electric field is equal to the force over the charge. Now, we don't actually have the electric field, but we do have the potential. There's a second equation that says that the electric field is equal to the change in potential over the distance. And so what that allows us to do is that allows us to make a connection between the change in potential and the electric force. So when we do that, we'll just go delta V over delta R is equal to F over Q. And then we can solve for the force, which will be the delta V, which is 150 volts. Sorry, I can read, I promise. Then we've got the radius, the distance between them, which is 4.50 centimeters, which that is 0.045. We're going to multiply by Q, and that then will give us the electric force. Now, we don't actually need that number. I know one of the concerns is, well, how am I supposed to do that if I don't have the charge? Well, remember, one of the cool things about the velocity selector is that the charge actually doesn't matter, because in the end, we want the force of the electric field to be equal to the force of the magnetic field. And the force of the magnetic field, if we take out all the absolute values, is Q V sine of theta B. And so you'll notice that they both have Q in them. And so the Q's are actually going to divide out, and the Q doesn't matter. That's why this is a velocity selector, because it doesn't matter what charge you send in, only charges with a specific velocity are going to come out. Now you'll notice that the sine of theta is going to be perpendicular. It does talk about those being uniform perpendicular fields. So the sine of 90 is 1, so that's essentially going to go away. And so we're just going to be left with here our 150 volts divided by the 0.045. We're also going to take this B and divide it over, so I'm going to go ahead and just put that on the bottom of my fraction as well. We're actually solving for B, so we're going to divide by the V here, the V which is 3.25 kilometers per second, so that would be 3250 meters per second. Remember, we want everything in SI, and therefore the answer should end up giving us the magnetic field there. So let's go ahead and punch all that in. We'll go 150 divided by, and I'll put in parentheses the 0.045 and the 3250 from our speed, and we get that the magnetic field is actually pretty strong, which is 1.025, so 1.03 Teslas. So we know the strength of the magnetic field that needs to be there so that my magnetic force will equal my electric force. All right. Now, the second question is show the direction of the magnetic field. Show how the magnetic field should point between the plates. Now, most people will be like, oh, well, if the electric field is up, the magnetic field should be down. No, don't do that. Okay, remember we need the forces to balance. So the electric force, let's say for a minute, let's imagine that my charge is positive. As it comes in, the upward electric field is going to apply an upward electric force, which in that case means that I need the magnetic force to be downwards. Now, in order to do that, I'm going to have to use my right-hand rule. Okay, now this is a little different than some of the other ones because we do have the velocity of the charge, which is coming in this way. I don't actually have the field. I'm trying to figure this out. What I do have is my thumb, which is the force. And so I need my velocity going this way, and I need my thumb to point in the direction that I want my magnetic field to be, which is downwards. So I'm actually going to have to rotate my hand like this to show that I have velocity this way, that the force is downwards, and you'll notice then that my fingers are pointing up out of the page, which means that the magnetic field should be coming out of the page, just like that. So out of the page. Now, you may say, but that's for a positive charge. What about a negative charge? Okay, well, let's look at a negative charge. Okay, so if a negative charge comes in here, the negative charge in this electric field will feel an electric force down. And so the electric force would be down on the negative charge. What that means is that we need the magnetic force to be up. Now for a negative charge, we can use our left-hand rule. So this is my left hand. Notice it has my watch and my ring, which my right hand did not. So I'm now using my left hand. Again, I want the velocity to go this way. I want my magnetic force to be upwards. So again, I'm going to have to rotate my hand so that my thumb is pointing upwards. And notice when that happens that my fingers are now pointing straight up towards you, which means that I need, again, the magnetic field to be coming out of the page. So I get the same answer no matter what. On an exam, if you recognize this as a velocity selector and you know that you're going to get the same thing no matter what, you don't have to do both of these. You can do one because you know that it's going to work for the other. All right? You can always double check it. There's nothing wrong with going through and saying, well, what about a different charge? But we do know that they're going to be the same thing. All right? So there we go. We've answered this question about a velocity selector. We found the magnitude and the direction of the magnetic field that is necessary to get those charges to make it through with a speed of 3.25 kilometers per second. That's pretty darn fast. Anyway, we'll see you next time.